is going to be asynchronous. So it's like our Wednesday, but it's going to be on Monday. And so we will be on campus the other 4 days of the week, and at least those of you who come to campus. And we'll go from there. So I will post an assignment for that day's work. I should have it into the classwork stream by Monday morning at the latest, the 29th, say a week ahead of time. So you'll have plenty of time to do it. You won't have to do it on Monday the 5th, but it has to be submitted by 3 p.m. on Monday the 5th for your attendance. So I will try to get that out to you a week ahead of time, because I know some of you are vacationing. Some people are already vacationing already, little stinkers. So must be nice. Right. So yeah, okay. That was physics. Sorry about that. And that is later. So let's get rolling and talk about van der Waals forces, whatever the heck those are. Oh, I lied. Before I forget completely, you need to staple your lab papers together. So those of you at home, you had the PhET simulation. You can submit the other lab as well, so it doesn't show up as missing. But I'm only grading the PhET simulation for those of you that are distance learners, so you know. So we have been talking about the bonding inside of molecules, intramolecular bonds. What's the matter? I don't want it. Oh, yeah. What were you doing while everybody else was doing that? Oh, you silly. Okay, gotcha. Makes sense. Silly goose. So electronegativity difference determines the character of the internal bonds between atoms, the intramolecular bonds inside molecules. And so carbon and oxygen, very much a polar covalent bond. Oxygen's winning the tug of war. Carbon and hydrogen, on the other hand, carbon's winning the tug of war. However, both of these molecules are not polar molecules. They have polar internal bonds, but the molecules themselves aren't polarized. How come? Nope. Gotta listen. They're not polarized. These are non-polar molecules. How come? The bonds inside are polar. They're even. That's a perfect way to say it. They're symmetrical. Okay? So this pull is the same as this pull, which means nobody wins the tug of war. All of these pulls carbons making on the hydrogens are equally spaced around the molecule, so it's non-polar. However, water and ammonia are polar. They have polar internal bonds, and the molecules are polar. How come? Because what? They have lone pairs. Dang, you're going to be a chemist. I'm going to get that. So they're not symmetrical. They're not flat. This is not flat, even though there's 3 equally spaced hydrogens. It's not flat and plane, and water is most certainly not equally spaced. So the question is, how do we make gases, individual molecules, coalesce into liquids and solids? And we'll come back to the perfect chord. There's a overarching generic term, which is a terrible term. Well, sorry, Mr. Johans. I'm sorry, your name is not terrible, but it's really kind of awkward. There are so many different scientists, old white guys' names that we use for science. It just kind of gets tedious and confusing. So van der Waals forces is kind of encompassing of all of these intermolecular forces. Again, these are what's going to allow solids and liquids to form. There's really only 2 kinds. Okay? We're going to hear about an extra important, strong kind of dipole-dipole interaction, but truly there's just dispersion forces and dipole-dipole forces that hold molecules together to make liquids and solids. Obviously, you guys can figure out he lived a long time ago. Thanks for your contribution, but it's much easier to say intermolecular forces than trying to remember all these people's names. However, this may come up in your college classes, so I want to be sure that you've heard it. Okay, so in the video you're going to watch here, Dr. McCord talks about 3 kinds of intermolecular forces. There's really only 2. Like, you know, scientists love to sort things, right? Plant, animal. Metal, non-metal, ionic, covalent, dispersion, dipole-dipole. However, one of these, like I said, is really important, and we'll focus on it, and focused on it already in biology, but I just want to point that out before you watch it.
Intermolecular forces are the forces in between molecules. In particular, we're talking about the attractive forces. The attractive forces between molecules is really what ends up governing all physical properties. And when I say physical properties, I mean boiling point, melting point, viscosity, surface tension, stuff like that are physical properties. And it's really governed by how strongly these molecules are stuck together. Turns out a lot of these intermolecular forces also affect the way chemicals react, because a lot of these same forces govern the way chemicals come together, and then if you can get them together, you have the possibility of a chemical reaction. We generally cover 3 basic...
So I just want to, it's fading away here, but it's got boiling point, melting point, viscosity, surface tension. Those are all physical properties. But how strong a molecule sticks to other molecules of itself, if it sticks strongly to itself, it's going to have a higher boiling and a higher melting point. It's going to take more energy to shake them apart. That's literally what you're doing. It's going to take more energy to shake them up. Surface tension will be on the next video.
Intermolecular forces that we give 3 distinct names. The differences are really pretty subtle. It all comes down to the difference of a positive charge and a negative charge. That's really what the attractive force is about. So you have positive and you have negative. The more positive it is, the more negative it is, the stronger the force. This is simply Coulombic attraction. Positive attracts negative. And we have all degrees of this. It's just a matter of how positive and how negative. Most molecules, being neutral species, do not have full positives and full negatives on them. That tends to be the world of ionic molecules. So we're constantly writing partial positive and partial negative. We even have the way we symbolize it on the paper, which you should be used to as these partial positive and partial negative charges. Matter of fact, if you can get enough distribution within your molecule to where you have a lot of positive charge on one side and negative charge on the other, you can get what we call a polar molecule. A permanent dipole is a polar molecule. And if you have a permanent dipole, you're going to have a setup within the molecule where you always have partial positive, you always have partial negative. And those are going to get together. That's called dipole-dipole interaction, and that is the strongest interaction you can have within a molecule to another molecule. Now, we have a subset of that that's actually the strongest version of that. They're even stronger than a regular dipole-dipole. And we call it hydrogen bonding. And it's really because it involves hydrogen being the partial positive part of this molecule. Anytime hydrogen is covalently bound to a very electronegative element, and I'll be specific here, it has to be bound to fluorine, oxygen, or nitrogen. When it is, it becomes so partial positive, and the oxygen or nitrogen or fluorine becomes so partial negative that you get an even higher amount of attraction. So we go ahead and classify that in its own class. We call it hydrogen bonding, but it's really just dipole-dipole interaction, just up a notch. At the low end of the scale are nonpolar molecules. Now, nonpolar molecules are molecules that have no dipole moment whatsoever. They usually are nonpolar due to symmetry arguments, meaning that whatever you argue pointing one way, there's the opposite way covered somewhere else on the molecule. So all the symmetry wipes out the polarity of the molecule. Good example of this is carbon tetrachloride. Carbon tetrachloride has 4 very polar carbon-fluorine bonds, but they all nullify each other as far as distribution of charge. So it's a nonpolar molecule. However, it will attract another carbon tetrachloride molecule. They do stick. It is a liquid. So there's definitely forces there. So what are they? They're dispersion forces, and they are based on what we say are temporary dipole moments. Temporary dipole moments is when the electrons within the whole molecule are in such flux that at any one point in time, you're going to catch it with a slight positive end and a slight negative. And another molecule is going to get caught in that same time, and there's going to be an attraction there. This will change over time and time again in very fast time frame, yet the attraction is there. So it's a very slight attraction. It's not nearly as strong as a permanent dipole, but that's what we call dispersion forces. So that's all 3 forces together there. We've got hydrogen bonding up at the top, right under it, dipole-dipole interaction, and a little bit below that, we've got dispersion forces.
So there, he's ranked them by their strength. It's like a factor of 10 each time. So if dispersion forces have a attraction of 1, dipole-dipole is 10 times stronger, and hydrogen is 10 times stronger than dipole-dipole, so it's 100 times stronger than the dispersion forces. So it gets dramatic difference, exponential scale. And they're not even close to being as strong as the bonds inside of molecules, however, ionic and covalent. All right, so van der Waals forces are called dispersion forces, or I can't see my screen on my laptop. So there's all these names. It's so freaking confusing, and I apologize. It's not my fault. Don't shoot me. So dispersion forces has to do with this dispersal, the movement of the electrons. So that's where that term came from. They're also called momentary dipoles, where for just a moment, all the electrons are on one side or the other, or more of them are on one side than the other. Some books call them instantaneous dipoles. Some of them call them temporary dipoles. They're all correct names. It's just pick one and just go with it, right? But they like to mix it up. But all of those words together mean the same thing. Some molecules have electrons that all kind of hang out, and then they move around. Remember, the electrons are moving always at the speed of light. So sometimes they'll cluster up on one side. Are they going to stay there very long? No, because they're all negative, so they're not going to stick next to each other. But that's a constant movement of positive and negative in the atom, in the molecules. Again, it's very weak, again, because they're moving around so much. And it is caused by the motion. So like carbon dioxide, we've said this is a nonpolar molecule. This molecule has polar bonds inside, but it's nonpolar. What state is carbon dioxide in at room temperature? Solid, liquid, or gas? Gas. Hopefully you're all breathing some out right now, okay? However, can we make it into a solid? What's it called when it's a solid? It has a special name. Remember, it's patented. Dry ice, okay? It's really cold, and it's not water, so it's dry. It's really silly, but you can make this into a solid. It's just not super easy. Just to confuse it even more, and I'll be perfectly honest with you, when I was in college, I was confused by this, but my professor called these London forces. So when you think of London, if you're like me, I think of London, England, London Bridge, but no, it's some other old guy last name. Okay, so it's like, oh, I felt so dumb when I realized that, oh no, it's not the place, it's a person's name. Anyway, okay, enough of that. So Paul Anderson calls them London forces. Some professors might. Just know that they're all the same thing: dispersion, momentary, instantaneous, temporary London forces. And they're all about moving electrons briefly from one side of a molecule to the other, creating that positive and negative dipole temporarily. All right, let's go with the real ones, the permanent dipoles. Those are the easiest to understand. There's a more positive side, there's a more negative side, and that's all about the electronegativity of the atoms in those molecules. They like to bunch together specifically because of opposite charges. This attractive force is much stronger because it's permanent, and it always stays that way. As Dr. McCord mentioned in his video, there is a special extra strong dispersion dipole force called hydrogen bonding, which I know you talked about in bio. And hydrogen bonding is super important because there's three atoms, three elements that really take this to heart in biological units like you and me: nitrogen, oxygen, and fluorine. And if you'll notice, they're all close together on the periodic table: nitrogen, oxygen, fluorine, fluorine, oxygen, nitrogen. Remember, fluorine's the highest electronegativity. Hydrogen's really a non-metal, even though it lives on the metal side, has one puny little proton and one stinking electron, so it's easy for big bully oxygen to grab a hold of that electron and make this side positive on a water molecule. Same thing happens for nitrogen. Nitrogen has an electronegativity of 3, hydrogen's 2.1. It can grab and take and hang on to hydrogen's electron. And both of these have, as Bethany told us, lone pairs. So these molecules end up being very polarized. And when you put ammonia and water together, so NH3 has the lone pair, it has that extra electronegativity, and the nitrogen, it can literally pull the proton off of a water molecule. Okay? And that's how we can form NH4 ammonium, that polyatomic ion. So when these two substances go together, that extra negativity is enough to pull the little tiny positive proton off. Kind of crazy stuff. And then you're left behind with hydroxide, which you guys might remember is a base, and that's why the stuff you use for cleaning, it works so well. All right, so cute way to remember which ones give you the hydrogen bonds. Hydrogen's fond of fluorine, oxygen, and nitrogen. Okay, make believe. There's no D on the periodic table, but you know, well, not D by itself anyway. He showed you the delta, the lowercase delta positive for hydrogen, delta negative for oxygen. Again, we can show that. But the fun part is with water molecules. So we started this section off with talking about snowflakes. So I'm going to give you a couple minutes to do this. We'll play with magnets. So I got these really nifty water kits, I don't know, with a grant a few years ago. And inside of these, they're very cute. They're like little sippy cups for kids, like at restaurants. It's very clever, I think. Are a bunch of water molecules. And so when you take them apart and play with them, you will notice that they like to stick to each other because they have magnets in them. So go back to your station. Also, there is a single unit of sodium chloride. See which side it likes to stick to. The sodium is the blue and the chlorine is the green. Go play, and I'll call you back in just a sec. Those of you at home, I'm going to play with you here after I turn off my microphone here so it doesn't kill everybody's ears. All right, so this is representing a sodium chloride crystal. I showed this to you guys earlier in the year, and they like to sit next to each other. Remember, when you hit an ionic compound, the ions repel each other, and that's why they shatter. And then these are representative of water molecules, the red end for the oxygen, the white end for the hydrogen. And they have magnets in them. And what's really cool is, and you've probably played with magnets before, you know that you put the white next to the white and they move. I hope you guys can see that. Let's get it out here. So, and the red end wants to be attracted to the white end. Of course, these are magnets. It's not really what's in a molecule, but it's close enough. So in order for water to solidify, it has to arrange itself a specific way. You can't just go any which way. And when you put all the water molecules together and make a snowflake, there's actually empty space, and that makes the volume larger, which makes the ice less dense and floats on water. Okay, it floats in the liquid, which is highly unusual. And then the other thing I just want to show you is the positive sodium ion is attracted to the negative oxygen end of water. The negative chlorine is attracted to the positive hydrogen. And so this is how water can actually pull apart ionic compounds. Okay. All right, I'm going to go back and then I'll return to you guys in this. All right, make sure all your water molecules get back in your cups. No. 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 Come on back. We got a couple more things to do. Get them all out of the sinks and off the floors and into the cups. It does? Oh, because of your battery? Yeah. Oh, that's all right. You can watch from the big screen. Yeah, smart. That's really smart. So water will bead up on things like this flower petal. You've seen that probably in your lifetime, or you'll bead on a car if it's wet, then like my car. So why does it do that? Because it likes to stick to itself, kind of like the magnets. Not identical, but it works pretty well. The fact that water likes to stick to itself is also useful when you want it to become unstuck and cool off. So the reason why perspiration works to cool you off, or why an evaporative cooler works, is because energy has to go into the water molecules and separate them. You literally are shaking them apart, okay? And then they can fly off as a gas. When they go flying off as a gas during the evaporation process, that takes the energy with it and leaves behind the slower moving, cooler molecule, so you feel cooled off. Kind of cool. Ha, ha, ha. So you know from back in grammar school about melting, physical processes, right? Solid into liquid. Liquid back to solid is called freezing. Evaporation is when a liquid becomes a gas without boiling. It doesn't have to boil to become a gas. Remember that. Of course you know that because you can hang your clothes out to dry. Condensation is the gas going back to a liquid. It takes energy being put into the system, has to be absorbed for the solid to become a liquid to become a gas. Well, guess what? That's called an endothermic process. Energy is going in. It takes energy coming out of the system for the gas to become a liquid to become a solid. It has to be released. So that means it's freezing is exothermic. It's really kind of weird when you think about it, but when you think about what has to happen, those molecules have to slow down. That means the energy has to leave them and go out in the system. So every winter, there seems to be a time when there's, not every winter, but lots of winters, there seems to be a time when there's going to be a big freeze during the citrus crop harvest. And so you'll see them spraying water, putting on the sprinklers onto the citrus orchards and all these orange trees and lemon trees having icicles all over them. And they did that to keep it from getting cold. It's kind of weird, but there's energy released. And then, of course, the ice makes a little bit of a protective layer. So let's talk about one last thing. One of my favorite TED Eds is this gal's discussion of water. Water is amazing, and we're going to learn more about it on Monday, but we'll get to, or Tuesday when we come back.
How come some insects are able to walk on the surface of a pond, but you quickly sink to the bottom when you try to walk on water? And why do lakes freeze from the top down in winter? In a word, the answer to all of these questions is polarity. Water is a simple molecule made up of one oxygen atom and two hydrogen atoms, but it is essential to life. In fact, water makes up approximately 60% of the adult human being's body weight. The polarity within those water molecules gives this common substance the properties that make it unique and life-sustaining. Polarity refers to the unequal sharing of electrons within a molecule. For water, the bonding between the oxygen atom and two hydrogen atoms within a single water molecule is like a tug of war between a big, strong football player and a cute little toddler. Oxygen is a larger atom with more protons in its nucleus than hydrogen. These positive charges are like a person's physical strength. They are able to attract the negatively charged electrons in a bond, just like a strong individual is able to overpower a weaker individual in a tug of war. So, oxygen is able to attract more than its fair share of electrons. Because hydrogen is smaller and has less strength, or fewer protons, it loses the tug of war and attracts fewer than its fair share of electrons. So the oxygen in water behaves as though it's negative, and the hydrogens behave as though they're positive. The bonds within a single water molecule are called polar covalent bonds. Covalent means that the electrons are shared. But, as we just learned, polar means that these electrons are not shared equally. In water, the oxygen acts negative, and the hydrogens act positive. Since negative and positive attract, that oxygen is attracted to the hydrogen atoms in neighboring water molecules. A special type of bond forms between water molecules known as a hydrogen bond. Hydrogen bonds don't just happen in water either. They can form between a water molecule and different substances that are polar or ionic. Water's ability to stick to itself is called cohesion, while water's ability to stick to other substances is called adhesion. Now, think back to the initial question. First, why are some insects able to walk on water? Surface tension due to hydrogen bonding creates a thin film on the surface of water that gives enough resistance for super light insects to walk on. You can't walk on it because the hydrogen bonds aren't strong enough to hold you up. Why does ice float on top of liquid water? For most other substances, the solid state is more dense than the liquid state. But that is not the case for water. Hydrogen bonds keep water molecules farther apart in frozen water than in liquid water. The farther apart the molecules are, the less dense that solid is. So ice is about 90% less dense than water, which means it floats on the top. That's why lakes freeze from the top down and aquatic life is able to survive through a cold winter every year. It is the polarity of the water molecule and the resulting hydrogen bonding that account for water's unique properties. So, the reason that water is so special, from inside your cells to the world's oceans, is simply because it is a polar molecule.
All right. So hopefully that was educational. So you saw firsthand how the water molecules, well, the magnets, have to expand a bit when you put them together. Questions at all right now? You have a exit ticket question for you to do. Please do that and submit before you leave. It looks like that. A little quick sign-off question. Make sure everybody's sticking around.